Firstly, thank you for all those involved in organising and for accepting my application to come and speak here. We're going to talk about wildfire now. This presentation is going to explore a number of lens-based and software-driven tools which can be seen to convert the heat and visual intensity of wildfire into a broad spectrum of functional imagery which are used for fire detection and fire suppression sort of purposes. The case studies are going to be drawn from the American West Coast fire scene. It's long shaped the national agenda in the country around environmental extremities. I want to argue how automated, algorithmic, or augmented images of fire produced by smartphones, surveillance systems, and predictive models consequently influence how wildfire should look, where it should burn, and how it should burn. In the autumn of 2020, images of an orange atmosphere pervading San Francisco began generating a discourse online about the inability to accurately document reality with smartphone cameras. This extreme atmospheric condition was formed by the coming together of airborne particulates from concurrent wildfires burning in 3 separate states. Converging high above the Bay Area and combining with the city's own pollution, the larger particles scattered the blue wavelengths of the sun's light, creating this hypersaturated, vibrant orange skyline. Particular attention was drawn online as to how iPhone photographs failed to capture environmental conditions which were visible to the human eye. Images were automatically desaturated, resembling something closer to that of an overcast, cloudy day. Computational photography has become commonplace in contemporary image making. Apple's Smart HDR feature, which was introduced for its portrait mode, which is now also used across all of the camera functions, is one of several automated corrective practices now appearing in digital photography processes. In pointing the smartphone towards the San Francisco skyline, the camera uses an algorithm called semantic rendering, which takes an input image and passes it through a neural network architecture to identify objects in the scene and apply different adjustments to each. It then performs a stylistic correction of the white balance, which is interesting in this context, measured in temperature, to produce images which Apple claims are more true to life. This feature extractor, or rather what the camera recognizes and sees, has been trained on a dataset of 4 million images and 1,500 classification labels. It's not surprising then that the unique orange atmospheric condition observed in San Francisco is misunderstood in this algorithmic view. Rising temperatures and human behavior has led to unprecedented incidents of wildfire, which no longer align with the expected data categorizations, thus evading their potential for image and scientific classification. Terms such as firestorms, firenados, pyrocumulus clouds, and now the provisionally named orange skies days are 21st century classifications of new environmental phenomena caused by the accelerating effects of climate change. Geographer Gregory Simon proposes that the desire to classify these new conditions with new terms reflects an increasing sense of threat and therefore a need to order and maintain them. Emerging in parallel to those environmental terms is a technical vocabulary of auto-enhance, color correction, white balance, which adds to the existing terms of dodge and burn to narrate a history of image-making practice which forego notions of objective reproduction in favor of a more aesthetically compelling visual registration. Fire has historically resisted documentation. Long before digital or computational photography, photojournalistic reporters using film long grappled with the difficulties of catching ephemera that behaviorally evades documentation. That is, fire is bright, fire is hot, and fire is fast-moving. Technological limitations inhibited photography's potential to provide evidentiary witness to fire's environmental significance. In these photographs from 1940, the presence of fire is demarcated by formless overexposure, which is void of information. This 1911 image bore no witness to the event at all. The smoke and flames have had to be painted onto the glass negative. In the case of the San Francisco images, the unprecedented evolution of fire into new unfathomable visual registers demands a re-evaluation of how humans document environmental change. The pursuit of software-driven advancements to achieve a more true-to-life documentation can not only be seen to affect how we classify environmental phenomena visually, but also semantically. The auto-correcting of white balance here represents a kind of environmental remediation, adjusting the threat of wildfires from an urban or environmental warning to that of an aesthetic nuisance. Where fire should be. The fire lookout towers that peer above America's forested areas are a marker of the nation's ambition to assert control over its natural landscape. From their peak of over 5,000 active lookouts, an estimated 300 remain manned in service today. Replacing them, the 21st century fire lookout tower is now a network of high-definition remote sensing cameras. Since 2013, over 1,000 of these cameras have been installed in remote wilderness areas of 8 states to make up the Alert Wildfire Network. Often appendaged to the retired lookout towers, these pan-tilt-zoom cameras continuously survey remote forest areas while being monitored by emergency crews on these wall-to-wall displays of playback monitors. Similarly to the level of attention required to man the lookout towers, the shortcoming of this new visual infrastructure remains human fatigue. At the current system scale, the sensor network captures 54 million images a day, demanding a near impossible level of concentration. Seeking to mitigate that potential for human error, machine learning classification softwares have been built to identify smoke plumes and anything else that's extrinsic to reference images of a calm, dormant forest, alerting the emergency dispatch centres when they do so. Still in their infancy, these systems have shown their limitations, most notably that of producing false positives. An estimated 1 in 20 of the automated alerts are actual burns. Clouds, fog, geothermal steam, dust kicked up from a vehicle, barbecues and dirty lenses have all tricked the camera vision into thinking there was smoke from a fire. Forest management officers are therefore required to manually confirm that a flagged image does include show smoke from a flame. Human observation and interpretation has always been essential in the accurate management of fire. Lens-based tools have, through the history of modern fire management, proven to supplement processes of observation, but not entirely replace them. The mid-20th century was a period of innovative optical research and development for the US Forest Service to improve their fire detection methods. So from mechanical panoramic cameras that could rotate 120 degrees per exposure, such as this one, to other finely calibrated mapping devices which could triangulate the directional bearings of smoke. This also included the short-lived but wonderfully named DetectoVision televised system of forest broadcasting, which in technological principle predicted the Alert Wildfire system which is in use today. As the conditions of fire have changed, the motivations and vested interests behind the desire for technological innovation have shifted over time. The extinguish at all costs attitude, which was known as the 10 a.m. rule, dominated the early years of modern forest management policy. It was conceived during a Second World War paranoia that fires could disrupt the war effort. As a result, fire was purely characteristic in destructive terms. As fire is vital to the health of most ecosystems, the forced removal of it has encouraged the proliferation of more flammable monocultures, resulting in larger, more intense burns. We've since abandoned the 10 a.m. rule, but rises in temperature today are causing larger and hotter wildfires to burn out of control. Parties commercially present in forest areas are having to share the growing financial burden of these changes. Policies related to risk aversion, culpability, and insurance are increasingly fostering a return to an attitude of total fire suppression. Utility companies are one of the actors in this economy. Aging or faulty infrastructure can sometimes play a role in sparking wildfire. Since 2018, Pacific Gas and Electric Company, which is the largest utility supplier in the country, has installed hundreds of their own cameras as a part of the Alert Wildfire Network. This coincided with the company's responsibility in igniting the 2018 campfire, which was the deadliest and most destructive in the state's history, for which Pacific Gas and Electric have since been convicted of 85 felonies of manslaughter, which is the deadliest homicide ever committed by a corporation in the United States. The presence of lens-based tools to survey the wilderness is an idea embedded within the history of forest management to speed up and refine processes of observation and fire detection. If the architecture of the lookout tower represented a wartime characterization of fire as a public threat to life, the 21st century virtual architecture of remote surveillance and computer vision reflects an increasing acceptance of commercial and personal risk in living in close proximity to a landscape which has a tendency to burn. How fire should burn. Effective forest management has always been aligned with the ability to predict how and when a fire might burn. In the last few decades, with the introduction of inexpensive computing resources, physics-based modeling softwares can be used to simulate how a wildfire might burn. Graphical representations of these predictions, rendered as 3D animations superimposed on GIS-based terrain models, have proven valuable in conveying technical information to the general public and assisting local response units during an active fire. The notable simulators, Farsight, Firelib, VFire, and Firetech, each share a common root in a set of equations derived 50 years ago by US forest science scientist Richard Rothermel. Season by season, however, wildfires are burning in unpredictable ways compared to those previously observed. Rothermel's model hasn't caught up with these new conditions, meaning existing virtual fire models are increasingly likely to falter. In attempting to keep up with this changing nature, new predictive systems are beginning to expand well beyond simply mathematical models. Ground and aerial-based methods of sensing and image production are being deployed to embed photo and video analysis data into the models to help fill some of these uncertainty gaps. Wrapped in fire-resistant aluminium enclosures, in situ devices, known as field fire behavior packages, are deployed in burning forest areas. Visible and thermal multiband video cameras are synchronized with various environmental sensors and probes to wirelessly allow for these devices to better evaluate fire behavior measurements in respect to flame characteristics and rate of spread. This on-the-ground visual data is combined with increasing granularities of other data sources measured by remote sensing devices, which include the measuring of atmospheric carbon levels, wind, humidity, and soil moisture, driving virtual models to a higher and higher standard of realism. As a consequence, attempts to increase the fidelity of the virtual fire are proving to be too computationally expensive for use in real-time fire response, due to the time that it takes to calculate and run the simulations, therefore establishing a trade-off between accuracy and real-world application. One of the key components in respect to both the scientific accuracy and the visual fidelity of the computerized wildfire is that of its virtual foliage. Early iterations of forest fire simulations represented trees as extremely simplified low polygon cones and cylinders, but contemporary fire models have progressed to include highly detailed 3D model assets for each species of tree, which have been purchased from commercial 3D modeling asset libraries. The computational trade-off is additionally constraining the virtual fire research areas to the order of magnitude of sort of 100 meters square, meaning you have these models that sort of float weightlessly in virtual space, as opposed to analyzing wildfires or predicting wildfires, which can be on a scale of, tens of hundreds of kilometers square. Completed with simulated smoke, flickering flames, and the graphic superimposition of burning patterns, the programs developed on the basis of scientific discovery are converging closer to the industry standard program for video games or cinematic visual effects. Users of the latest models, which run on video game engines, can simulate the use of fire retardant, or they can cut down trees to create fuel breaks. In this gamified logic, if fire can be virtually ignited, then it can be virtually extinguished. This apparent shift in objective is reflected in the academic journals in which developments to fire models are being disseminated. This includes Computers and Graphics, Software X, and Transactions on Graphics publications, rather than the long-standing International Journal on Wildfire or Fire Ecology, for example. To many fire scientists, the danger with these advancing virtual simulations is not necessarily that they're inaccurate, because all models are fallible, is that they're focusing more on the problem of technology than that of science. What one reporter referred to as the field's obsession with modelling suggests a technological fallacy exists in which the pushing of the visual reenactment of fire's flame towards a higher standard of mimesis equates to greater knowledge. Emphasis should rather be placed on whether Rothermail's 50-year-old mathematical framework, which fundamentally structures these models, is fit for purpose in the 21st century fire ecology. Rothermail's models were developed when stricter dividing lines were drawn between that of the built and the natural environment. No contemporary virtual model currently captures this changing interface. Flammable structures, such as houses, are not included in their simulation, nor are the non-linear effects of how we live, work, and operate socially in proximity to forested areas. This includes questions of resource extraction, land use, policy regimes, insurance and tax mechanisms, as well as socio-cultural behaviours such as acts of landscape beautification and acts of arson. The supposition that a wildfire can be faultlessly accurately modelled, simulated, and reenacted virtually contradicts the wildness of wildfire's own etymology. Images of fire are the primary way in which the general public experience or understand the notions of threat, risk, and environmental significance that wildfires represent. Extending the preeminent fire ecologist Stephen Pine's formulation that contemporary fire ecology can be understood as a cultural conception, these examples seek to extend this to a network of image-making apparatus that mediates fire today as a connected landscape of visual and semantic relations. A close reading of the automation, enhancement, and optimization of fire imagery points towards a technological fallacy existing, whereby the fidelity in which we are able to accurately program and reproduce fire through lens and technological interfaces equates to an improved ecological understanding and therefore the increased capacity for management. The effects of this are a misaligned public cognition to the heat of the 21st century environmental urgency to reconsider how we build, live, and operate within wildland areas.